Hello and welcome to the lecture on density and pressure. Okay, well, this is going to be our introductory lecture on fluids, so we're going to introduce a lot of terms, some of which we'll use later in the chapter. All right, so first of all, let's define what is a fluid. Well, a fluid is anything that's not a solid. That, of course, includes gases and liquids. Okay, so both gases and liquids are fluids. Why would we lump them together? Well, fluids create drag forces, they exert pressure, and they flow according to streamlines, at least under ideal flow conditions. And so in that sense, both liquids and gases do the same thing. Now, there are some things that gases don't do. When we talk about heat exchange, we'll talk about gases separate from liquids. But here, for the dynamics, the kind of forces aspect, and the pressures that result from those forces, it makes sense to lump together liquids and gases and call them fluids. Okay? Hopefully that's clear. Next up is the term density. We've used density before, but kind of just as a supplemental idea, here it's front and center, crucial to our understanding of dealing with all of the ideas of fluids. And what it is mass per volume, so kilograms per cubic meter. Water has a density of about 1,000 kilograms per cubic meter, and air has a density of 1 kilogram per cubic meter. So water is 1,000 times denser than air. These are kind of rounded numbers, but they give you a good idea about those two very common fluids that matter interacts with here on Earth. All right, and a density of 1 gram per cubic centimeter is not equal to 1 kilogram per cubic meter, but instead 1,000 kilograms per cubic meter. And that's because there are 1,000 grams per kilogram, but there are 1,000,000 cubic centimeters per cubic meter. And because of those different conversions, we obviously can't keep the ratio the same. So sometimes you might see the density of water reported as 1 gram per cubic centimeter, or you might see it other times reported as 1,000 kilograms per cubic meter. Those are the same, okay? All right, and there are other ways to measure density, which you'll see in some examples throughout this chapter. But we can always convert them back over to the standard unit of kilograms per cubic meter, using the standard base units. All right, well, another term that comes up is the idea of specific gravity. Well, this is a density comparison to water. So it's actually a ratio. It's dimensionless because it's a density divided by a density. Notice here I'm using the Greek letter rho for densities. Okay, that's the letter you have to get used to using for at least volumetric densities. But sometimes we don't really want anything with units at all, so we just take a ratio. So if something is denser than water, then the ratio would be greater than 1. And if the density is less than water, then the ratio would be less than 1. All right, and it's represented with the two uppercase letters SG for specific gravity. Okay, now atmospheric pressure is a particularly important pressure value. It represents the average air pressure at sea level. Okay, and it's taken to be 101,325 pascals. The Pascal is the Newton per square meter. We'll see that when we talk about the definition of pressure in our key formulas, but that is the derived unit. Pascal is the metric unit, and then in terms of, well, simpler derived units and a base unit of meters, we can express it as, well, if you think about it, force per area, which makes sense because that's what pressure is. It's force per area. Okay, so atmospheric force per area is 101,000. Okay, it's a big number. It is represented by the unit of 1 atm, so that's a common kind of alternative way to measure pressure. It can also be represented as 760 millimeters of mercury, Hg being the scientific name for mercury, like on the periodic table. A millimeter mercury is also called a torr. I won't use that unit, but it's good if you've seen it before. But here we'll be using millimeter mercury, although of course we'll primarily be using pascals because we try to stick with the base units. Okay? Now, if we're talking about pressure, including atmospheric pressure, we might want to consider gauge pressure versus absolute pressure. What's the difference? Well, gauge pressure is measured relative to atmospheric pressure. So, for example, in a pressurized tank, okay, that would be the gauge pressure in that tank, right? A gauge pressure would be the pressure you take on a tire, right? You actually measure it with a gauge, hence the name. On the other hand, atmospheric or absolute pressure is measured relative to a perfect vacuum, usually kind of thought of as outer space. Outer space is not a true perfect vacuum. There's always some sort of interstellar medium or interplanetary medium, some very, very low density gas. But, you know, it's pretty darn close, and you could always consider some place that is a perfect vacuum, and then that is where absolute pressure is measured relative to. So, for example, if you had a gauge pressure of 1 atmosphere, then the atmospheric pressure or the absolute pressure of that tank then would be 2 atmospheres because you'd add 1 plus 1. All right. So next up is another form of pressure called hydrostatic pressure. Hydro's got water in the name and static because it's at rest. It's the pressure that's created from depth in a fluid. So as you go down deeper and deeper into a fluid, usually water, then your hydrostatic pressure grows. We're all aware of this. So by swimming down into water, you feel it in your ears, right? So that's hydrostatic pressure. Okay? The deeper an object is submerged, the greater the hydrostatic pressure exerted on that object. It is a form of gauge pressure because it's measured relative to atmospheric pressure. Okay? Now, it's kind of a special case of gauge pressure, but it definitely is, right? Because it's not an absolute pressure. It's always measured relative to the atmosphere. Okay? Next up is something called a manometer. Now, a manometer is just a U-shaped tube, plain and simple. But it's kind of helpful for considering some examples that we're going to do in terms of comparing densities and pressures. So it's a device used for measuring relative densities between fluids that do not mix. That's one of the examples that we'll see. And it can also be used to measure pressure when one end of the U-shape is closed and sealed off. All right, so that's a manometer. You'll see some diagrams of it in the examples. Last up is Pascal's principle. Well, this is a principle that refers to the transmission of fluid pressure. Now, really, you can kind of think of it as a conservation of pressure law. So conservation of pressure law. It's not maybe the most accurate title for it, but it helps relate it to conservation laws we've seen before, like conservation of energy, because the idea that is in a confined fluid, pressure is the same at every point. So here it is in the formal definition. It states that a pressure change at a point in a confined fluid is transmitted throughout the fluid so that the pressure change is identical everywhere. All right? So that's the idea, that any change at one point is the same as the change at any other point. It's not force that's the change everywhere, and that's important because Pascal's principle allows us to understand the ideas of hydraulics, which is a fluid-driven lever. In other words, you put a little bit of force in and you get a big force out, which is fine as long as you give something up, and we'll see what that indeed energy is still conserved, and you have to give something up, just like with a lever. You have to give up the convenience of being able to push close to something. You have to have a really long lever arm. You have to have the fluid equivalent of a really long lever arm when we're applying Pascal's principle. Okay, so the application of Pascal's principle is probably what you will remember once you leave the class. But ultimately, it is all about the transmission of fluid pressure in a confined fluid. Okay. So those are all our key terms. Some of them, are more broad than others, but hopefully it sets the stage for discussing fluids. Okay, so now let's get to our key formulas, more just about basic definitions of working with fluids. Okay, so first up is density, right? Density is represented by the Greek letter rho, kind of looks like a curly P. I draw mine like these to not confuse them with e's. Okay, all right, it is mass per volume. Mass in kilograms, volumes in cubic meters, thus density is in kilograms per cubic meter. No special name for that unit, it's just kilograms per cubic meter. Here we have specific gravity, right? It is a ratio, for example here, a density of an oil compared to the density of water, okay? Now specific gravity usually has a density of about 850, oil has a density of about 850 kilograms per cubic meter, so then its specific gravity would be what? 0.85, okay? Which means it would float. That's the idea, but of course, oil does float on water. All right, so there we have our ratio of densities called specific gravity. We compare to water because water, of course, is ubiquitous and important. Next up is the definition of pressure. All right, so pressure, right there, measured in units of pascals, okay? PA, right, is a derived unit. I know it's an unusual derived unit because it has two letters. We've never seen that before, but it is a derived unit just like a Newton or a joule. And it is a Newton per square meter. If we were to think of it in base units, since the Newton is the kilogram meter per second squared, and then we're dividing that by square meters, we see we're left with the kilogram per meter second squared, or kilogram per meter second squared is the Pascal. So it's the mass per length per time squared. But that's really strange, kind of hard to internalize. It makes a lot more sense to think about it as force per area. And so we see it expressed that way much more, or just expressed as PA pascals. All right, so there it is, force, and then area. Okay. All right, next up is hydrostatic pressure. Okay, so that's a special type of gauge pressure, and it is entirely due on the depth you go down into a fluid. So look at what it's dependent on. It's dependent on the density of the surrounding fluid. So, for example, the density of water, 1,000 kilograms per cubic meter. It's dependent on the gravity, so it would differ on, if you are on a planet with more gravity, then going down into water would have a bigger effect. Your hydrostatic pressure would grow more quickly. But on Earth, of course, gravity is just 9.8 meters per second squared. And then the only other term that shows up here is the depth. So that tells us that it doesn't matter the size of the body of fluid that you're submerging an object in, it only depends on the depth. But that makes sense, right? Because when you swim, say, 10 feet down into a pool, you feel the effects of pressure on your ears just as much as if you swam 10 feet down into a lake. Of course, the lake is much more massive, it has a much greater cross-sectional area, but the cross-sectional area has no effect on the hydrostatic pressure because pressure, by definition, has divided away the effects of area. In fact, there is a term for this. When you have a unit which takes another unit and divides by something, well, dividing by that something is called normalizing to that quantity. So pressure is normalized to area because we've divided by the effects of area, thus eliminating their importance. Okay? That's, at least one very useful way of thinking about pressure. All right, next up is absolute pressure. You see it in the subscript. Okay? So P, sometimes might be shortened as ABS, but absolute pressure is the sum of gauge pressure. I think the subscript G is clear that it stands for gauge, and then ATM for atmospheric, which definitely is always the acronym you're going to see for atmospheric, or the shortening of the word. Okay, so that's absolute pressure, gauge pressure plus atmospheric. Okay, next up is Pascal's principle, which says that the pressure out equals the pressure in. And you could also think of it as pressure at point A equals pressure at point B, right? So, it's often, out and in, but it could, just be some individual points. The out and in usually refers to some sort of movable pistons, which are the main examples that we're going to see, because then we're really using Pascal's principle in a hydraulics type of setting, okay? And then, since P out equals P in, it can be rewritten in terms of ratios of forces. All right, so this is just Pascal's principle rewritten. How do we write it like that? Well, P out equals F out times A out. P in equals F in times A in. When you just cross divide by the forces in the areas, then you get all the forces on one side and the areas on the other, and you get a ratio that looks just like this. All right, so in other words, the ratio of forces equals the ratio of areas. So if your area out, so if your output area is much larger than your input area, then your output force, so your output area is much larger than your input area, then your output force is going to be correspondingly, as a ratio, much larger than your input force. That's your force multiplying. That's the way to get more force out than you put in, which is, like I said, is the same idea of a lever, right? You can push on a lever of a certain amount of force, but then at the end of that lever is doing much more force. That is a mechanical advantage, is the actual engineering term for that. But here we're seeing the hydraulic version of mechanical advantages, just like a lever. Okay, hopefully that makes sense. I mean, I think it's such an important idea. That's why I'm calling special attention to it. All right, well, let's get on to our practice problems. There's simple problems because this is a very introductory section here, just laying down mostly the definitions and the basics of fluids. All right, we'll get into more complex examples later in the chapter when we talk about buoyancy and fluid flow. Okay, so what are our practice problems? 4 types. Simple problems that involve using the definition of density or pressure is type 1. Type 2 are simple problems that involve calculations of hydrostatic pressure, including in a barometer. Type 3, problems that involve using a hydrostatic pressure to compare between fluids in a manometer. Right, that's going to be our U-shaped tubes. That's kind of a particular type of problem, so I want to call attention to it. And finally, type 4, problems that involve using Pascal's principle to relate forces within a fluid where cross-sectional area varies. All right, that's going to be our hydraulic levers. Okay. So before we get on to actual numerical problems, let's do some quick concept questions to make sure we're good on the ideas of densities. All right, so let's change some densities. Question 1, part A. Imagine that through some sort of process such as thermal expansion of a solid or heating of a gas, and that's actually what we're going to see in chapter 10, an object is increased in length, width, and depth, all by a factor of 3. Will the density change? By what factor will it change? Well, yeah, if you don't change the mass and you change the volume, then of course the density will change because the density is mass per volume, right? All right, so we're going to compare the initial density, so P with a subscript 0, to the final density, P with subscript F. All right? Okay, so then density is mass divided by volume. All right? So here, these are divisions, but they're going to cancel out. All right, so we're interested in the ratio here. All right? So then we look at the ratio. We have then that we're going to have a 1/27 change in terms of the change in volume. All right? So in other words, the new volume will be 27 times, or the new density will be 27 times less than the original density, and that's because we tripled each of the dimensions. And by tripling each of the linear dimensions, our overall effect is 3 cubed, all right, or a 1/27 factor change. Okay? All right, moving right on to part B. What if the length is increased by a factor of 3, but the width and depth are only increased by a factor of 2? Well, in that case, it would just be 3 times 2 times 2, which is 1/12. So then our density would decrease by a factor of 1/12. Okay? So in other words, or a better way to say it, would be 1/12 its original density. Okay? Now, what if the object was a circular cylinder with a radius that increased by a factor of 4, but a length that only increased by a factor of 2? So again, we're expanding things, but keeping the mass constant, so we should expect a correspondingly decrease, as just like the other two, decrease in density. All right, will it be smaller or larger than others? Well, let's see. Well, since it's proportional to the ratio and the ratio is squared, we have to remember to square our 4. So when we square our 4, we get 16. 16 times 2 is 1 over 32. So actually, this was the most dramatic decrease in density to a density that's only 1 over 32, the original density. All right? Okay, so now let's look at our first actual quantitative example. And it should be a straightforward one. If a certain metal has a specific gravity of 7.99, so that means it's about 8 times denser than water, then what pressure will the bottom side of a 1 cubic meter cube of this metal exert on the ground? Okay, so that's the idea. And metals can definitely be in this density range. They can be even denser, but this would be typical of a fairly dense metal. Okay, all right, so then use the definition of pressure. Pressure is force per area. Force is just mg, in this case, gravitational force, divided by the area. The area would be one side of a cube. One side of a 1 cubic meter cube is 1 cubic meter raised to the 2/3 power. That works for cubes. And well, that's actually just still going to be 1 in this case. And so then we're just going to get the pressure, which is going to be the density times the volume times g. Well, where did that come from? Well, I just replaced mass with density times volume, which of course you can do because after all, density is mass over volume. If I cross multiply by volume on both sides, I get that mass is density times volume. This is a relationship that comes up a lot. It may be obvious, but it's good to call some attention to it because a lot of times we're going to replace m in equations we're familiar with from previous chapters, replace m with rho v, okay? And of course you multiply by g because we want a force, not a mass, and we divide by area, okay? And then here I've just plugged in the numbers. I changed my specific gravity of 7.99 to actually units of kilograms per cubic meter by just multiplying by the density of water. That's how my specific gravity became 7,990 kilograms per cubic meter. Multiply by the volume, multiply by gravity, and divide by the area, which is just 1 raised to the 2/3 power, which is 1. And there we get 7.83 times 10 to the 4 pascals, or 78,300 pascals. Okay? And that's the force per area on that side of the cube pushing on the ground, right? Newtons per square meter. Okay, example 2. If we assume that your head and shoulders have a cross-sectional area of 0.2 square meters, which is fairly accurate, then how much force is pushing down on you due to the atmosphere above? So in this case, we're going to take an atmosphere, a known atmosphere, atmospheric pressure, 1 atm, and multiply it by an area in order to get a force, right? So the idea is that force is pressure over area. Now, you might be like, wait, aren't we going to be usually solving for pressure given a force? Well, yeah, but sometimes you might want to go the other way. Sometimes you're given a pressure, given an area, and instead you need to find the force. And that's exactly what's happened here. So we'll take our known pressure, atmospheric pressure at sea level, at least the average value, multiply by the cross-sectional area of your head and shoulders, and we get 2.02 times 10 to the 4 newtons. That's actually a lot of force. That's 20,000 newtons. That's the weight of a large car sitting on your head all the time. How can we withstand such a huge force? Well, there's a number of reasons. First of all, we've evolved to withstand that force, but that's kind of a simple explanation. How in what ways have we evolved to withstand that force? Well, the nature of tissue is very strong to that, and also we are pressurized. Okay, now being pressurized isn't counteract it. We're absolutely used to things pushing down on us. The atmosphere pushing down on us, and that of course is in addition to the fact that we're being pulled down by gravity, but the fact that we are pressurized is no joke. If you put a human in a vacuum, they would triple in volume. Okay, all right, so example 3. All right, so now we're on to discussing hydrostatic pressure kind of on its own and in the context of a barometer potentially. So a barometer works by balancing a column of fluid with hydrostatic pressure equal to atmospheric pressure. So the idea there is you just need a certain depth that equals the depth of the atmosphere. All right. So considering that mercury has a density of 13,560 kilograms per cubic meter, which would be a specific gravity of 13.6 approximately, how tall would a column of mercury be in a barometer? Okay, so the idea here is we want atmospheric pressure to equal hydrostatic pressure because barometers are all about balancing those two. Because otherwise the mercury would spill out of the barometer because all barometers must be open at some point, usually a small hole, but they are open to atmospheric pressure. So then if we solve for the height of Hd, which is the name for mercury, so solving for the height of the mercury, we take atmospheric pressure and divide by the density of mercury and gravitational acceleration, and we get a height of 0.760 meters or 76 centimeters or 760 millimeters. That's where the term comes from, or the common unit to express atmospheric pressure the typical value, we say the atmospheric pressure is 760 millimeters mercury because of mercury's common use in barometers historically, not as common today. Okay, so that is a barometer made out of mercury, which is the most dense common fluid out there. Okay. Now, what if instead we wanted to replace the mercury with water and make a column of water that worked like a barometer? Well, in that case, we'd have to solve for the column of water. The only difference here is we would replace our density for mercury with the density of water. So we'd replace the 13,560 with a value of 1,000 kilograms per cubic meter. So obviously, it's going to be a much taller column of water, right? We're going to get a much larger h because we're dividing by a smaller number. And indeed we get a height of 10.3 meters. That's why you don't see a lot of water barometers, because they'd have to be over 30 feet tall. They wouldn't really fit in many places. All right, so the idea here then is, what does this really mean? What does it mean to be balancing something, getting hydrostatic pressure in a column and having an equal atmospheric pressure? Well, it means that we have a column of some denser fluid equal to the column of air that we are all at the bottom of. Well, how tall is the column of air of the atmosphere? This big idea up, until we get to outer space. Well, it doesn't exactly work that way, because in order for it to be a uniform column, we'd have to be assuming constant density. Air, being a gas, is actually quite compressible. That's where the whole maybe lumping together gases and liquids into fluids doesn't work quite right. But overall, the value is about 100 kilometers is the height of the column of air that we are at the bottom of, thus giving us our, hydrostatic pressure from air. Okay? Okay. So again, that's considering the idea of hydrostatic pressure in the context of barometers. Okay, so example 4, if the gauge pressure of a scuba tank is 25 kilopascals, so that's a pressurized tank, right? Obviously scuba tanks are pressurized. What is the absolute pressure of the fluid inside that tank when it's used at a depth of 25.5 meters? All right, and here we're going to use the density of seawater, which is a little bit denser than our typical go-to value for water, which is 1,000, which would be pure water. Okay, all right, so we're going to take absolute pressure as the sum of the gauge pressure plus hydrostatic pressure. Collectively, these two are all gauge pressure, but we're calling special attention to the hydrostatic form of gauge pressure, and then plus atmospheric pressure to compare it to the vacuum of space, quote unquote vacuum of space. Okay, so here we have the pressure inside the tank plus the pressure at that particular depth, which is just density of seawater times gravity times the depth, 25.5 meters. All right, and then we get a final value of 3.83 times 10 to the 5, so about 3.8 atmospheres. Okay, so we'll say about average 3.8 atm. Okay, so quite a bit of pressure, all right? And as far as this idea, right, about hydrostatic pressure and comparing it to atmospheres and pointing out that this is not quite 4 atmospheres, but still is a very large value, and then, thinking about our imaginary water barometer, which would be impractically tall, well, this number also has another kind of convenient meaning, one thing you can think of. You can think if you swim down to a depth of 10.3 meters, so if you swim down, just over 30 feet, obviously pretty deep, then you'd be doubling the pressure on your body. You'd be doubling your normal pressure that we're used to handling, which is why it's such a big deal. Why it becomes quite painful at weak points like the eardrums to experience that dramatic increase in pressure. Is it possible to swim deeper? Yes. Obviously you can do it in a pressurized suit, but even free diving, you can swim deeper than that, but you better practice because it's hard to handle that increase in pressure. All right. Okay, so let's move on to a next form of examples. These are examples that involve manometers. Okay, so example 5. 2 fluids are poured one at a time into a U-shaped glass tube, a manometer, of constant radius. The fluids do not mix. The tube is open on both ends to the atmosphere at sea level. When the fluids are at static equilibrium, the liquid Y is 4 centimeters above the flat line, as shown, and the liquid X is only 2 centimeters above the line. If Y is water, all right, so now we know what one of the mystery liquids is, then what is the specific gravity of the other liquid? Okay, all right, well, we should be able to find it. So the idea is we're going to use a force balance and also acknowledge that this dotted black line is a line of equal pressure, which makes sense because if the forces are balanced, the pressures must be balanced as well. Okay, and so for equilibrium, we know that F net equals 0, and so then we're going to set F up equal to F down, as shown here in blue. And so then we're going to have the mass of the water times gravity equals the mass of X times gravity. All right, because essentially we're saying that this must balance this. All right, so then you have the density of water times the volume of water times G. That's just replacing M with rho V. And then over here we have the density of mystery fluid X, the volume of mystery fluid X times G. G's cancel. And then we're going to rewrite the volumes as H times A. The cross-sectional areas cancel as well. And then we're just going to be left with finding our density of our mysterious fluid, which is just going to be the density of water times the height of the water divided by the height of X, which we see then is just going to be the density of water multiplied by 4/2, which is just going to be multiplying by 2. But that makes sense intuitively because this liquid, we only needed 2 centimeters of it to balance 4 centimeters of water. So that means that this liquid is twice as dense as water. Okay? So, very simple result, very intuitive result, but we see where it comes from. Also notice that we took a force approach here. We could have also just set the pressures equal to each other and just use the hydrostatic pressure, rho GH, from the beginning and actually ignored a cancellation of areas. That's important because in reality, the areas are not going to matter. Here I wanted to show that they naturally cancel out for a tube of uniform density, but since we know that the hydrostatic pressure is dependent on depth only, even if the area changes, the pressure will not. Okay, because again, pressure is force per area. So by its very nature, we divided away the effects of area. Okay, so keep that in mind because that does beg the question, well, then how does area matter? Okay, well, we'll see when it does and how it does. But first of all, let's look at example 6. Consider a manometer as shown. Okay, this one's a bit different because look, it has a sealed end. All right, the left end has been closed and partially evacuated, so we pumped out some of the air, right? And partial evacuation, we do this all the time, like think about using a straw. You create a partial vacuum in your mouth, thus drawing the fluid up the straw, right? Not a perfect vacuum, but a partial one. If the fluid in the tube is seawater and has a density of 1030 kilograms per cubic meter, and the height shown is 4.15 meters, that's H, then what is the pressure at points A, B, and C? Okay, so for A, the pressure must be atmosphere because it's open to the atmosphere. Okay, there's nothing to change the atmospheric pressure. What you might say, oh, well, maybe this is below the sea level. Well, yeah, a few centimeters below sea level is still effectively sea level. So this is definitely atmospheric pressure at 1.01 times 10 to the 5 pascals or 101,000 pascals. All right. What about B? Well, B is on a horizontal line like this. That means that B must be the same pressure. Okay, so it's on a equal pressure line, just like in the manometer above. All right. So we can go ahead and show that we can solve for that pressure and cancel out, right? Or we could just say they're at the same depth, so they must be the same. Okay? So again, both approaches work, and that it kind of shows some idea about where the derivation of hydrostatic pressure comes from. It comes from this idea of taking a force balance, okay, and showing that the area is independent of the area. All right? But what about point C? Because point C definitely is not going to be atmospheric pressure, unlike points A and B. So what is it going to be? Well, here, let's again use a force balance because that's kind of been our approach so far. We're going to consider pressure up times area and pressure down times area. Area is going to cancel. So then we're going to replace pressure up with atmospheric pressure minus the depth. Why minus the depth? Because we've gone up. Now, we're used to usually adding hydrostatic pressure for, to compare something. But here we're subtracting it because we're actually going the opposite direction. We're losing that gauge pressure here, the special type of gauge pressure called hydrostatic pressure. Okay, the pressure due to depth. And that's going to then equal P down, which is the pressure at point C. So in other words, the pressure at point C is just going to be atmospheric pressure minus the hydrostatic pressure. Okay, because we went up, right? Point C is above it, right? So this then is going to give us a value that is less the atmospheric pressure because, of course, point C is at the fluid-fluid interface, the air, the partially evacuated air, water interface, seawater interface, that is balancing it out. Okay? And so there we get 6.9 times 10 to the 4 pascals, right? Just over 1/2 an atmosphere. Well, I'd say significantly over 1/2 an atmosphere, about 70% of an atmosphere, right? Because it's about 69,000 pascals, where 1 atmosphere is 101,000. Okay? All right. Does that make sense that it's less? I hope it does. Okay? Less an atmosphere, that is. Let's do our last concept question. And this is going to be a segue to our last type of quantitative question, which is using Pascal's principle for those hydraulic levers. Okay. So, question 4. The example above shows a relatively tall column of water being displaced by a short column of mercury. Does the cross-sectional area of the different sides of the manometer affect the heights of the respective columns? No, definitely not. Hydrostatic pressure is independent of area. P1 equals P2, right? We have this idea that we have an equal pressure line. They have to be equal to each other. In other words, the hydrostatic pressure density of mercury times gravity times the height of mercury, right? A small height must be equal to the density of water times gravity times the height of water, a much larger height. The area cannot matter. The fact that A1 equals A2 can't matter. But what about the forces, right? Because the forces must also balance each other. F in must equal F out. Notice I'm using F in and F out because that's the terminology of Pascal's principle. Again, a segue to the next and last topic. Okay? So then what effect does that cross-sectional area have, right? Because this is a special manometer. This manometer is specifically designed to have lopsided cross-sectional areas on either side of the U. Okay? Well, let's see how it matters. Okay, so what effect does the differing cross-sectional areas of the manometer have on the forces pushing up on the water column and the mercury column? Here it is. The force pushing on the mercury column of height h is greater than the force pushing on the water column, since Pascal's principle tells us that the forces must be equal to each other. And indeed, we see in the definition of hydrostatic pressure, again, that they must be equal to each other. So that means that something else must be different. And indeed, it's the force, because the force in is F in over area, and the force out is F out over area, which means that F out is going to be equal to A out over A in times F in. Well, A out is a much larger value because that's A1. A in is the smaller value, A2. So then A out over A in, so A out over A in as a ratio is a value greater than 1. I take a value greater than 1 and I multiply it by whatever my force in value is, which is just the weight of the water, and I'm going to get F out, the force pushing on mercury, as a bigger number. Okay? Absolutely. So that means that this is a force multiplying manometer, and the mercury is being pushed on by a greater force than the water is pushing at that equal pressure line. Okay? So this is absolutely a lever, a form of a lever, okay? And what might be kind of throwing you off, you might be like, well, that's great that the force pushing out is bigger, but look, there's so much less mercury. But remember, mercury is 13 times denser than water. So the fact that this is, yes, a much shorter column doesn't matter. If it was a much shorter column and was the same cross-sectional area, if A2 was equal to A1, then the forces would be equal to each other, because then you would have a very short and not very wide amount of mercury that was being supported by the water. But here you have a appropriately short column of mercury, but a wide column of mercury, which required that force multiplication, which was due to our unequal areas in the manometer. Okay? All right, well, let's do it with some numbers. Maybe that will make more sense. Okay? All right, so last two examples involving Pascal's principle. So example 7. Consider the apparatus shown below with a confined fluid. If the surface area of the small piston on the left is 3 square meters, and on the right it's 113 square meters, which seems big, but after all, that's 10 by 10 meters, which is big, but the idea is this is a very effective hydraulic system. Then how much force must be applied with F1 to achieve F2, so a push up at F2 of 25,000 newtons, or 25 kilonewtons? Okay, well, we're just going to use Pascal's principle, P out equals Pn. All right, rewrite P out as F out over A out, and P in as F in over A in. All right, and then cross multiply to solve for F in, because that is our unknown force, to find out how much force we need in order to get our desired output force. All right, and so then we're just going to rewrite it in terms of the actual subscripts shown in the figure. So replace all the ins and outs with ones and twos, and then we'll plug in our numbers. All right, so we know that area in is our 3 square meters. We know our desired output force is 25,000 newtons, and our output area is 113. So there we go. We find that our input force need only be 660 newtons in order to get 25,000 newtons of pushing force. That's a big force multiplication. We're getting a huge amount of force for relatively small input force. All right, this is like a human level of pushing force. You could actually push this just by putting your back into it, really pushing as hard as you can. All right, that's 660 newtons. And then you get enough force to lift a car, 25,000 newtons, okay? So that seems great, but it also seems like we're getting something for free. But of course we're not. There's nothing for free in physics. Example 6, or example 8. All right, what do we have to give up? Well, if you wanted to use a similar apparatus as the one shown above, so all the same areas, okay, to lift a car with a mass of 1,100 kilograms resting on the right. So imagine now, put a car over here, okay? Then how much force would you have to apply to the left? Okay, so to solve for a new force given a particular output force. And then something new, how far would you have to push the left piston in order to lift the car 1 meters? That's a thing, right? Because maybe it would be more than a meter, right? Let's see. All right, so first of all, part A is going to be just like example 7 above. We're just going to go ahead and solve for the input force in order to lift the car. In this case, our output force is going to be mg, right? Because instead of just giving it as a force, we're given a mass. So now we know it's going to be about 11,000, right? About 11,000 newtons, right? So less, right? And we find that we only need 268 newtons, right? So a very moderate force in order to lift a car. Remarkable, all right? But now let's remember that Pascal's principle in no part said that it violates conservation of energy. So sure, we see now something new, conservation of pressure, but we still have something old, conservation of energy. And specifically, we're going to use conservation of energy in the form of work out equals work in. Because at no point can energy be magically created between points 1 and 2. Thus, the work done on the car must be the same as the work done in pushing the smaller piston, right? They must be, right? So that means that force in times distance in must equal force out times distance out, just using the definition of work as force times distance, all right? So then if I solve for the distance in order to get a lifting distance of 1 meter, then I put my F out, which I know to be about 11,000 newtons or 1,100 kilograms times 9.8 meters per second squared, divided by the F in that I found through conservation of pressure or lossless transmission of pressure, and then solve for that distance. What are we going to get? A really big number, 37.7 meters, well over 100 feet. All right, so that means that you'd have to push this piston really, really, really far in order to get a very small lift there. And in fact, the bigger the force multiplication, the more dramatic the really long push that you need in order to get a really small push on the output. Right? So that's what you give up. You give up distance. Now, of course, in actual mechanical devices, we can have lots of little small pushes in some sort of ratcheting system. Right? You can think that that's the way a lot of hydraulic levers work. So there's plenty of ways around it. Force multiplication is still wonderful, right? But it doesn't come for free. You do have to give something up, and it's distance that you give up because energy is conserved. Okay. Well, I hope that this introductory lecture on fluids has been interesting and informative. Thank you so much for watching.